Welcome back. Let's start with the following theorem. This is known as, I'll call this subgroup test 1. Let G be a group and H be a non-empty subset of H. If H is closed under the operation and the inverse, then H is a subgroup of G. In other words, to show that H is a subgroup, according to this test, all we have to show is one, AB is in H for all AB in H, and A inverse is in H whenever A is in H. So this test tells us that to show that a non-empty subset H is a subgroup of a group G, we have to prove 1 and 2. It's enough to prove 1 and 2. Okay, let's prove this, why this test is true. So the assumptions of the test are 1 and 2, right? So assuming 1 and 2, we want to show that H is a subgroup. Well, notice that 1 says H is closed under the operation, and 2 says that each element of H has an inverse. So what remains to show that H is a subgroup? Well, does the associative property hold in H? Well, we know that it holds in H automatically because H is a subset of the group G. And so the only thing that I really need to show is that the identity belongs to H. And so let's try to prove that. Now, H is a non-empty subset of G, so H has at least one element. Let's call that A. So let's say A is an element of H. And since H is closed under the inverse, we know that A inverse belongs to H as well. So that by 2, we know that inverse of A belongs to H. And but now, since H is closed under the operation, that is by 1, we can say that A multiplied by A inverse, which is the identity, must belong to H. So we applied number 2 first, and then we applied number 1 to show that the identity belongs to the subset H, and that shows that H is a subgroup of G. So again, this test is telling us that in order to show that a non-empty subset H of a group G is a subgroup of G, we have to show 1 and 2. Here is our subgroup test 2, and what it says is that, again, let G be a group and H be a non-empty subset of G, and if AB inverse is in H, whenever A, B are in H, then H is a subgroup of G. In additive notation, instead of writing AB inverse, we would be saying A minus B. Now, this is a one-step subgroup test. The previous one, you can call that a two-step subgroup test. This is a one-step subgroup test. And I'm not going to provide a proof of this. You can read it from the text. So this is simply saying that to show that H is a subgroup, you have to prove only one thing, which is AB inverse is in H whenever A and B are in H. This one is called the finite subgroup test. So if in case the group H is a finite subset of G, in that case, to show that H is a subgroup, all we have to show is that H is closed under the operation of G. So when H is a finite non-empty subset of G, then to show that H is a subgroup, all we have to show is that H satisfies the closure property. Again, I'm going to skip the proof here. All right, so let's do an example. Let's say that I want to show that the following. So let's let G be an abelian group, and let H and K be subgroups. HK is defined to be the set of all products H times K, where H is in H and K is in K. And we want to show that HK is a subgroup of G. Again, what is so if an element belongs to this set HK, then that element is equal to H times K, where H is in H and K is in K. Okay, so we're going to use the one-step subgroup test here to show that HK is a subgroup of G. First, I want to show that HK is non-empty. Well, remember, so H is a subgroup and K is a subgroup of G. So each one of them contains the identity E. So because each one of them contains the identity E, then HK, one element of HK, you can think of that as E times E. So then I see that the identity is in HK, and as a result, HK is non-empty. Okay, so now let H1 K1 be an element of HK, H2 K2 be another element of HK. So that would mean that H1 H2 belongs to H, and K1 and K2 belongs to belong to K. So since G is abelian, we know that H2 times we know that the inverse of H2 K2 would be the same as H2 inverse times K2 inverse. Okay, so now I'm multiplying H1 K1 and the inverse of H2 K2. And because G is abelian, we know that this inverse is H1 K1 times H2 inverse K2 inverse. Since G is abelian, we can reorder the factors in this product. So that is, we can bring H1 and H2 inverse together and K1 and K2 inverse together. So we can rewrite this, and we can see that H1 K1 H2 K2 inverse is equal to H1 H2 inverse times K1 K2 inverse. Now, because H is a subgroup, it is closed under the operation, so H1 H2 inverse belongs to H. Similarly, K1 K2 inverse belongs to K. So we see that this is an element of HK, and therefore this element here is an element of HK as well. So what have we shown? We've shown that if I pick two arbitrary elements of HK, so I picked A is equal to H1 K1, one element of HK, and B is H2 K2, another element of HK, and then we showed that A B inverse also belongs to HK. So by the subgroup test 2, we see that HK is a subgroup of G. That's the set of exercises. So here we are taking H to be the set of 4 matrices, and this is going to be a subgroup of GL2 of R. And remember, GL2 of R is the collection of all 2 by 2 invertible matrices, or it's the collection of 2 by 2 matrices with non-zero determinant. And if you look at the set H, there are 4 matrices here. This one is the identity matrix, and each one you can check that the each one of the matrices here has an inverse that is in this set, and so this is going to be a subgroup of GL2 of R. So this is a finite subgroup of an infinite group GL2 of R. Let H be a set of all. Let H be the set of all diagonal matrices in GL_n of R, so since the matrices in GL_n of R invertible invertible, the diagonal entries must all be non-zero here. So the H is the set of all diagonal matrices where none of the diagonal entries are zero. Then H is a subgroup of GL_n of R, and the reason is H would be closed under multiplication, that is the product of two diagonal matrices is diagonal, and also the inverse of a diagonal matrix is also diagonal. So H would be a subgroup of GL_n of R. Okay, so I'm going to stop here, and in the next video we will be looking at subgroups generated by a single element.